Hello and welcome to a calculus lesson on continuity. This is lesson 3b, the second lesson of topic 3. We'll learn about continuous functions, combining continuous functions, and the intermediate value theorem. Let's get started. The phrase continuous functions is kind of vague to me. It forces me to ask the question, what's the difference between continuous on an interval and a continuous function? Think about it. Is there one that's more specific or one that we appreciate more? By the way, in calculus, we also care about continuity at a point, but I covered that concept in lesson 3a. From my experience, the difference between these two ideas is a fine detail, possibly very fine. When we're working with functions, we should be skeptical that they meet all of the conditions required to move forward with a problem. That means we might avoid saying that a function is continuous in general. But what we really mean by a continuous function is a function that is continuous on its domain. For example, the parabola y equals x squared is a continuous function. Its domain is all real numbers, and it's continuous from negative infinity to infinity. The reciprocal function y equals 1 over x is also continuous on its domain. The domain excludes x equals 0. It's continuous from negative infinity to 0 and 0 to infinity, exclusive of 0. We could also say that 1 over x is continuous on the closed interval 1, 4. The nice thing about that is we mean exactly what we say. We'll use this idea of continuous on a closed interval when we look at the intermediate value theorem. Another function to consider is the tangent function. Tangent x is continuous on its domain, which is all real numbers except for odd pi over 2's. So 1 pi over 2, negative 1 pi over 2, not in its domain. 3 pi over 2, negative 3 pi over 2, not in its domain. Like 1 over x, tangent x has an infinite discontinuity. In fact, it has an infinite amount of infinite discontinuities. Tangent x, you're so meta. I'll wrap up this concept with a controversial statement. A continuous function can have a point of discontinuity. What? It's because when we say continuous function, we actually mean continuous on its domain, which means that that could exclude some x values. Thank you. I told you, it was controversial. And it's a very fine detail. Okay. Now, just a short thought on combining continuous functions. First of all, combining functions means that we're adding them, subtracting them, multiplying them, or dividing them. There's also that unique way to combine functions. It's called composition, when we plug one function into the other as the x value or input. Now the question becomes, can the combination of two continuous functions be discontinuous? Oh gosh, I'm sorry for even asking that. It's so ambiguous based on the very definition of continuous function that we talked about a moment ago. So I will not even get into what happens when we add, subtract, multiply, divide, or compose two functions that are continuous and see what happens based on all of their specific domain issues. The important thing here is what happens at a specific point. If f is continuous at a specific point, x equals c, and g is continuous at that same point, then the composition of the two functions, g of f or f of g, is also continuous at that point, c. However, we should still be skeptical. I'm thinking, how can we make this general statement about g and f? What if g has a square root in its formula? F of x is a rational function where we could have a divide by zero situation. Then I realize that if f and g are continuous at x equals c, that means they're both defined at that point. Then we could be comfortable with this conditional statement. We can use the fact that the functions are continuous to move on with a theorem, like the intermediate value theorem. Or later, when we're taking derivatives, we can actually move forward with the derivative. The intermediate value theorem is the last concept to cover in this lesson. It's also the first key theorem to know and understand in calculus. It goes like this. If a function f is continuous on a closed interval, we'll call it a comma b, then the function takes on every value between f of a and f of b. The theorem is simple, intuitive, and useful. I want to point out that the hypothesis of this theorem is that the function you're working with is continuous on a closed interval. In other words, the function being continuous on an interval is the condition of this theorem. Let's look at a quick example. V of t is the velocity of a car at time t. Selected values for v of t are shown in the table. What must be stated in order to conclude that there exists a time c, so time equals c, such that v of t is 75? Using the information from the table, I'm picturing a car starting at a stoplight. The light turns green, the car speeds up, and we're given some data points over the next 20 seconds, 5 seconds at a time. After 10 seconds, the car is going quite fast. So maybe the driver took a ramp onto the highway, got up to around 78, maybe even 80 miles an hour at time equals 17, and then slowed down because the speed limit was 70 or 65. I'm realizing now that velocity as a function of t is a continuous function, and that's exactly what needs to be stated here. V of t is continuous on the closed interval 0, 20. Therefore, there exists a time c such that v of t is 75. In fact, I think there are two times, around 13 seconds and maybe around 17 seconds. And that's it. There are a variety of these types of questions. This one is sort of backwards, but there are other ones where they give you the condition that the function is continuous and you need to make the conclusion. You could also be given a function instead of a table of values.